Assalamualaikum warahmatullahi wabarakatuh. My name is Ashfi Fazlin bin Jasmine, DE210 Forces. Now I want to present for task 1, analysis of electric field between electrodes by using FEM software. First, we need to draw these two electrodes with radius 25 cm. We open FEM software. We select the problem, which is electrolysis problem. We press tab and put the coordinate for electrode. We connect these two dots and we draw the semicircle 180 degree. And for this problem, we need to set in centimeter. Okay, for the first case, is the gap distance is 1.0 cm and the voltage is 31.4 kilovolt. Okay, we need to put the information in this software. For conductor, the HV part we add HV. The voltage is 31.4 kilovolt, and we add property for ground 0 kilovolt, and then we add material for air and boundary. We name it as open boundary, and we input the coefficient. Now we declare the line open boundary. The first conductor is HV, another one is ground, and we put air. Okay, we need to save the file before run. Okay, we run the solution. Okay, this graph, this image is for voltage. Now we change to field intensity. Okay, we get this image for this conductor for 1.0 gap distance. Okay, to view the graph, we select these 2 points and we choose magnitude of field intensity, and we get the graph for 1.0 cm gap distance. With the higher voltage we get is 3.17 megavolt. Gap distance 1.5 cm. Okay, we back to our conductor. We just select two dots only, which is this node and this node, to move 0.5. We select D and move. We edit the vertical shift 0.5, and we get the 1.5 centimeter gap distance. And don't forget to adjust the HV value, which is 44.7 kilovolt. Okay, now we just run the simulation. Okay, we can see this image for field intensity, gap distance 1.5 cm. Okay, we see the graph. Select these 2 points. We select the magnitude of field intensity. Okay, we get this graph for 1.5 cm gap distance. Okay, we can see this graph, the higher value for this graph is 3.02 megavolt. And we repeat this process with the other value of gap distance. Okay, next for gap distance 2.0 cm with 58 kilovolt. This is image for gap distance 2.0 cm for conductor, and we see the graph is graph field intensity. The maximum value we get is 2.95 megavolt. Okay, next for gap distance 2.5 cm with 71.5 kilovolt. Okay, this is image for conductor gap distance 2.5 cm, and this graph for magnitude field intensity. The maximum we get is 2.92 megavolt. Okay, next gap distance 3.0 cm with 85 kilovolt. Okay, we get image for this gap distance like this. For the graph, we get the maximum magnitude field intensity for gap distance 3.0 cm is 2.89 megavolt. Okay, next for gap distance 3.5 cm with 97 kilovolt, we get this image for the conductor like this. And for the result in graph field intensity, we get the upper bound for this graph is 2.84 megavolt. Okay, for gap distance 4.0 with 110 kilovolt, we get the result for image is like this. And the result for graph magnitude field intensity, for the upper bound we get 2.83 megavolt.
Assalamualaikum and very good morning. My name is Muhammad Anis Mustaqim bin Muhammad Syaimi and my metric number is CE210. Okay, so we look at this. This is in field intensity. So to look for the voltage, this is the voltage. But in our case, we want to see the field intensity. Okay, then to came up the graph, just press here and here. Then press. So we got the Emax versus length of the gap. Okay, next we do the 7.5 centimeters. So just use the 5.0 centimeter file. And then what you need to do is just need to reset this. Reset. And just repeat this. That's the still out of the system. This is the ground. This is the fish. That is memory also that find this system. Give you 9 and this one. So we go to still and just make the things. So that's all for this mission. Thank you.
Okay, for introduction, electrical engineering relies on the analysis of electrical fields, especially for managing high voltage transmission lines. This knowledge helps identify high electric stress areas that could cause system failures or public safety risks. Using sphere gaps for evaluating electric fields and calibrating device is crucial for efficient management. Peak high voltages are measured, and engineers can ensure the reliability and security of power transmission infrastructure by tracking and managing electrical stress. Okay, next for objective. First, understand electric fields by use finite element analysis to study electric field in electrostatic problem, focusing on the sphere gap setup. Second, create finite element analysis model by build up a model with material properties, boundary condition, and mesh generation to simulate electric field distribution between electrodes. Third, analyze electric field by study electric field distribution between grounded sphere gaps to find areas of high electrical stress and risk. Lastly, apply safety measures. Guide action to prevent physical damage and ensure safe, reliable high voltage transmission line operation. Okay, for method, in task 1 involve modeling the electric field between electrodes in sphere gap arrangement using the finite element method magnetics FEMM software. The geometry of the electrodes and material characteristics such as potential difference between electrodes and grounding one terminal are created. A mesh is created for finite element analysis and making electrostatic problems. Analysis identifies area with significant electrical stress, guiding correction action to prevent system breakdown. Students learn how to use FEMM software for electric field analysis in practical engineering applications.
And next, I will discuss about the discussion of our laboratory. So the study analyzed the relationship between voltage, gap distance, and maximum electric field in high voltage systems, particularly those using sphere gaps. The voltage needed to start a spark rise in proportion to the gap distance, but the voltage rise is less noticeable as the gap distance increases. Conversely, there is an inverse correlation between gap distance and Emax, as the electric field intensity decreases as the distance increases. This is due to the lesser concentration of faults per unit area at any one place. Variables like the spheres, diameters, and environment can affect linear pattern in breakdown voltage and Emax distribution. Electric field concentration, sphere size and curvature, humidity, and air pressure also impact this number. Understanding the interaction between the voltage gap distance and Emax is crucial for designing reliable and safe high voltage system. So as you can see, this is our result for the laboratory. So when the gap distance is increased, the Emax dimension is decreased. Decrease slightly, for example 3.7 to 3.02, 2.95 to 2.92. So there is slightly decrease for every gap. And this is our FEMM simulation result for Emax simulation. For example, this is for 17.5 cm. Next, for our discussion on field uniformity. Okay, field uniformity is crucial for safety and performance in various fields like particle accelerator, medical equipment, and material processing procedure. It ensures consistent field with a specific area, ensuring accurate measurement and reliable measurements. Factors such as boundary circumstance, material quality, and source geometry influence uniformity. Techniques like numerical simulation, shielding, and electrode design can help achieve uniformity. However, achieving complete uniformity can be challenging due to trade-off between strength, uniformity, and complexity and performance. So this is our difference between gap distance 1.0 to gap distance 17.5 here. As you can see, there is for the graph here, the graph is the same, but the value is different. For voltage, the gap is the same, but the value is different due to the applied voltage. For example, for 17.5 we apply voltage 362K, but for 1.0 is 31.4K. And for the Emax versus gap distance, the start of graph is a small graph, but there is like distortion. There's not uniformity in the gap because there is decrease Emax when the gap is bigger. And so as you can see, the result is also show that when the gap is near, there is stronger Emax, and when the gap is longer, there is less Emax. In conclusion, this study promises a throughout understanding of electric field behavior in the sphere gap setup. The cornerstone for ensuring the safety of high voltage transmission line, finite element analysis or FEMM will be harnessed to construct a meticulous model that integrates the crucial material properties of the system component. Realistic boundary condition will further enhance the model accuracy. Reflecting the true operating environment, this intricate model will then utilize to analyze the electric field distribution within the sphere gap. The analyze will be paramount in identifying in high stress region, pinpointing area with the greatest potential for breakdown and catastrophic failure by progressively addressing this high risk zone through corrective action such as optimizing electrode geometry or implementing installation strategies. This study will provide invaluable knowledge. This knowledge will ultimately serve as a powerful tool for safeguarding the operational integrity and reliability of high voltage transmission line, guarantee the uninterrupted flow of electricity. That's all for the task 1. Thank you.
Hi and good day everyone, my name is Ishalini Murugan from Group 2 Section 2. So now I would like to explain step by step to do task 2 of lab activity 2. So first here we choose new and magnetic problems, and here we choose problem, and problem type is planar, the length unit is centimeters and the depth is 1, okay. And now we would like to set the coordinates for the material. So here we choose the draw knot and tap. So the first coordinate is x0, y0. So we zoom out to see the knot here. And the second one is x10, y0. Next one, x0, y10. And the next one is x10, y10. Okay, now we draw the line. We choose this draw line button. Okay, so we draw the line here. Okay, so for the second layer, we choose the draw knot button again. So x10, y9, x1, y9, x1, y1, and x10, y1. So these parameters are based on the length given in the lab sheet. Okay, so we draw the line again for the second layer. Okay, so now again we are going to draw the I core here. So we choose the draw knot here, tap, x10.1, y10, x11.1, y10, x10.1, y0, and the other one is x11.1 and y0. Okay, so we draw the line again. We can zoom it out. Okay, so now we are going to draw the coil. So again we choose the draw knot button, tap, x1, y8, x2, y8, x2, y2, and x1, y2. Okay, this one is for the right coil, so we draw the line. And the same thing we're doing for the left side of the coil, which is x0, y8, x -1, y8, x -1, y2, and the last one is x0 and y2. So we draw the line again. Okay, so now we are going to set the properties. So we go to the properties, materials, and here we have no material, so we have to add it up. So properties, we cancel this first. Properties, library. So we drag and drop air first, and the second one is copper AWG. So we choose 10 AWG, and the other one is this one, metal handbook DC magnetization curve, and we choose M50. This is also based on the lab sheet given. Okay, so now we press the green button here to set the materials, green. So we select the core, we right click and enter the space button, and we choose here the material is M50. Okay, so for the I core we do the same thing here, right click, space, M50. Okay, and for the coil we choose properties, circuit, and here we also don't have anything, so we have to add property. Here we choose coil circuit, series, and 50 amps. Okay, so we choose the green button here to the coil first for the right one, right click, space, here we choose 10 AWG, and circuit we choose coil circuit, turns is 500 based on our lab sheet. And for the left coil we do the same thing for the block type, we choose the same thing for the block type and also the coil circuit, but for the number of turn it is -500. Okay, so now we go to the for the boundary condition, we go to the knot and set our coordinate, which is 30 and 0. And the other one is x negative 30, y 0. So this is to make a circle around our material. Okay, so we zoom out a bit so we can see the knot here. And we have to draw arc from here to here. And the arc angle is 180. Okay, and for the bottom, for the top arc, we choose from right knot to the left knot, 180 also. Okay, so now we go to the properties, boundary. We choose add property, and here we name it as boundary condition. Okay, so now we right click on the rod on the top of the arc. We right click, space. So here we choose the boundary condition. Okay, and same thing for the bottom arc. We choose boundary condition. Okay, now as we can see, our material here is not centered. So to centralize our material, we group our material. So we choose this group button, and we choose this rectangle dotted button to group our materials, and we choose the move button here to move it. So here at horizontal, we choose negative 5.05, and for vertical shift, we choose negative 5. Okay, so now our material is centralized. So first we have to save our file before proceed to cracking. So save first at desktop. Okay, save. And next we go to the green button here. Okay, we choose the green button here and put it into the center of our material. And right click, space, the block type is air. Okay, so now we press the crack button here to run the results. After that, we choose the glasses here. So after we press the glasses button, we will get our result. So we can zoom and see the flux line. And to color the region, we can choose this color button here and show density plot. Okay, so this is the final result. And to see the force exerted on the I core, we can press the green button here to select the core, and we press it here, and we choose integrate. Here we choose force via weighted stress tensor. Okay, so here is the force exerted on the I core, X component and Y component, which is horizontally and also vertically. So that's all for task 2. Thank you.
Salam sejahtera and hello. My name is Yashinda Sanalaki, and Canada's matrix number is AE 2020. I'm going to present to you the introduction of task 2. The complex interactions between magnetic materials and electrical currents in the field of electromagnetic frequently reveal amazing events. Here, we examine the details of the C2I core system, in which the 50 ampere direct current is carried by the C core, which is carefully wound with 500 turns of 10 AWG size cable. Next, the objectives. Firstly, examine the C core's magnetic characteristics using 500 turns of cable that is 10 AWG in size. Secondly, examine how the activated windings magnetic field affects the I core, which is the load. Lastly, investigate whether changing the current or winding arrangement could be used to regulate the magnetic attraction between the C and I core. Moving on to the methodology. In task 2, we were required to analyze a C2I core model to be used as a prototype for a magnetic lifter in our customer's factory. Firstly, we started to design the C core on the magnetic problems page, and then we placed the coordinates for the C core, which were then being connected one by one until the complete C core is created. Nextly, the discussion. In task 2, there are 3 main components, which are C core, I core, and the coils. In this task, all the material and condition setup were done completely to the C to I core before cracking the result. Moreover, the horizontally and vertically exerted forces on the I core are negative 145.087 Newton and 0.0159492 Newton attracted toward left, respectively. From this reading, we could observe that the horizontally exerted force is greater than that of vertically exerted force. So, as a conclusion, the overlook about the C to I core system has offered a deeper understanding about the intricate nature of the electrical currents and magnetic interactions. Our increased comprehension of this phenomena opens up new avenues for creative developments in everything from magnetic levitation to power electronics, which in turn leads to the creation of more reliable and effective technologies. That's all from us. Thank you.